Welcome to Module 4, Lesson 8, Percent Error Problems. Okay, so there probably will be or will arise a good reason to be studying this right now. Probably a little bit of a precursor to statistics and error analysis and such. So seems kind of, as I see it, right now seems maybe a little bit misplaced overall. So, but we will see in the future. But anyway, get ready. This is could be challenging content, but that's okay. Don't fret. Okay, just follow the process. Look for shortcuts, and make sense of it all. Okay, so first a few definitions, and we will have these. We will see these definitions again during the lesson. Okay, let's go ahead and talk about these two here. One is called absolute error, and hopefully you are noticing that word absolute. You might remember it from absolute value. Okay, and that is very pertinent. Okay, because absolute value will be used in finding absolute error. Okay, and so so absolute error is given the exact value x. Okay, and x is just what we're using for exact. Okay, of a quantity and an approximate value a. Okay, so you can see that works out well. A for approximate of the quantity. The absolute error is, and you can see it there, absolute error is going to be the absolute value of A minus X. Okay. Now, just this whole idea of these exact values and approximate values. Okay. I mean, exact value. Let's say the first example we're going to see is the measurement of a computer screen. Okay. When a computer screen is, for example, there are 15-inch computer screens, okay, like I have in my Chromebook. Now, that 15-inch computer screen, we want to believe that it is going to be exactly that, okay, when they produced it, high-tech manufacturing, etc., we are trusting, okay, that it's 15. So that would be the exact value, the value they have on the box. Okay, now this approximate value might be a value that our children may get, or we may get when we measure, when we do the measuring, okay? And which is always up for possible error, okay? Just based on where we placed our ruler or our measuring tape, might have just had it in the wrong place. And when we're talking about very large things, very small amounts don't mean very much, okay? Don't make a real difference, but when you make, let's say a heart surgeon makes a centimeter error on where he snips some valve or snips some artery or whatever, I mean, that makes a big difference, okay? So this idea of absolute value, okay, or not absolute value, but absolute error, okay, is real important, because that there is a level of error that is up to a certain level of error percentage is allowed in some professions. Beyond that, it's not allowed, or it's unadvisable. Okay, but anyway, so we're figuring out this absolute error. Here is our formula, and again, it's the absolute value of our approximation. Okay, and the exact measurement, the difference between those two. And truth is, we're going to see eventually that this is going to be the same. Okay, those two are equivalent, all right, because we have our absolute value signs. Okay, and as we had mentioned early on in Module 1, this idea of this subtraction, this difference, okay, it's the actually the length or the area, the distance between, okay, so the distance between A and X is going to be the same as the distance between x and a. It's just that in this occasion, a minus x might give you a negative value, and x minus a might give you a positive value. So, for example, let's just throw one out there. And again, we're going to see these a lot, but I just wanted to talk about it a bit. Let's just say an absolute value was 8 inches was the measurement, 8 inches, and the actual exact value was 9 inches. Okay. All right. So if we went, and again, this was A, and this was X. Okay. So if we plugged it in here, absolute value of 8 minus 9, which is the absolute value of -1, which is 1. Over here, if we put absolute value of x minus a, is the absolute value of 1, positive 1, which is also 1. Okay, so you can see that they are the same. And that's why we use the absolute value signs when we are figuring out these absolute errors and percent errors. Okay, it's so that we always end up with a positive number here. Okay. All right, so percent error just continues on with that. The percent error there then is the absolute error is of the exact value. Okay, so right here, let's use our example right here. We have our absolute error is 1. Okay, all right, and then we had so here, I'm sorry, the percent error is the percent of the absolute error is of the exact value. So we're comparing that absolute error to, in this case, it would be the exact value. Okay, the exact value. Therefore, if we do, absolute value of, again, 8 minus 9, okay, and I'm just doing right here, and then we're going to put that over the x, okay, which is the exact value, right? All right, so that's going to be 1 over 9, or 1/9, okay? 1/9, and if we turned 1/9 into a percent, let's see, what would we have here? Have it done this? 1 divided by 9, what do we have? I know I should know this. Ninths ninths are interesting. I think it's like, keep going, a lot of ones. Oh, that's right. That's what ninths is. Ninths is 1, 1, 1, 1. It's a actually non-terminating decimal. Just 1 repeats, so we would just call that, go out to just basically we could say 11, maybe go to a point, 11.1%. Okay, so that would be our percent error, would be 11.1%. in this case. Okay, and again, we'll do a lot more of these. I just wanted this to be an introduction, just so it doesn't seem confusing when we get into it. Okay, so we're going to do a little practice problem here. Okay, and I'm just going to, and again, in the classroom, excuse me. You can imagine we could all have our Chromebooks up, and I could ask 3 of you to measure your screen size. Now, interesting thing about screen size measurement, if you didn't know this already, but screen size, a computer screen size is actually measured. If you didn't know, and you probably didn't, because it wasn't too long ago that I learned it, but it's actually measured diagonally. Okay, this is your screen size right here. When you say screen size, it's not a horizontal right across the middle line, okay, or vertical. Okay, it is a diagonal measurement. Okay, so that's how they would measure your screen, from one corner to the other. Okay, so anyway, we would do that, and we might get data like this. Okay, Taylor. There is no Taylor. There's no Connor in our class. But anyway, so Jordan, I wanted to erase that. So we have 3 students, and pick you out of a hat and decide who's going to take these measurements. And then we have Taylor. He takes measurement 1. He gets 15 and 2/8. And measurement 2 gets 15 and 3/8. Okay. Always good to measure twice. They always tell you, if you hear any carpenter, one of the rules of carpentry is to measure twice, cut once. Okay, if you measure once, you end up cutting maybe several times and maybe several different pieces of wood. But anyway, yeah, so measuring twice. Now he measured twice and he did get different values. For the sake of our problem here, we're just keeping everything in terms of eighths. Okay, so we're not actually reducing this 2/8 here. We're just keeping it at 2/8 instead of reducing it to 1/4 as we could. But just for this measurement, this problem. Okay, and now again, our exact measurement that we're actually comparing these two, okay, is 15 inches. Okay, so this is the exact measurement, all right? Because we see on the box, this computer came in a box, and it says this is a 15-inch screen. Okay, all right. So Connor does it, and he gets the 15 and 4/8, and then he gets 14 and 7/8, which is quite a big difference. Who knows what he did? He might have done something drastically wrong. Jordan as well gets two pretty diversely different answers as well. Okay. Now with here's absolute error again. Okay, so if we can go ahead, we can calculate absolute errors here. And again, just to repeat, given the exact value x, which is this here, is 15 inches, and an approximate value a, and all of these here that are on this table are approximate values. Okay, we can calculate our absolute error for all of these scenarios here by doing taking the absolute value of a, which is the approximate value, the measurements that the kids made, and subtracting x, or the exact measurement. Okay, so in this case we're getting we're left with a whole number. Okay, or not necessarily a whole number, but could be any rational number, because of course it could very well be a fraction. Okay, and then when we get to percent error, we'll be looking at a percent. Okay, so let's go ahead and use those table values and calculate some absolute errors for the following problems here, following measurements here. So let's go ahead and look at Taylor's measurement 1. And again, let's go ahead and write up our formula here. So our absolute error formula is going to be the absolute value of the difference between the approximate amount and the exact measure. Okay, so approximate and the exact. Okay, and that's it right there. So let's go ahead and look at Taylor. His measurement 1 was 15 and 2/8. Okay, let's go ahead and look at that again. So we have the absolute value of 15 and 2/8 minus 15, which is our exact value because we're looking at a 15-inch computer screen. Okay, and now again, just to reiterate, again, we're in a classroom, I might ask questions about this, but I'm just going to state it as a matter of fact. Well, let's go ahead and do these side by side. So just to tell you that I could also do it, 15, absolute value of 15 minus 15 and 2/8. Okay, let's just watch. And again, we did this already, but just to reiterate, just to tell you now, in this case, we just do the absolute, we do a minus x to make it simple, to keep it consistent, but truth is, it could be absolute value of x minus a. Anyway, let's go ahead and do that. So in this case, we have the absolute value of 2/8, okay, and here we have the absolute value of negative 2/8, and those are both equal to 2/8 inches. Okay, so we have an absolute error for Taylor's measurement 1 as 2/8 inches. Okay, 2/8 inches. Now, 2/8 inches, if we want to break that down, we know is a 1/4 inch. Okay, that's a 1/4 inch, right? Which is a measurement we would see on a ruler, for example. Okay, we could also break that down, or not break it down, but look at it in terms of a decimal value, and we can say it's 25 hundredths of an inch, okay, as a decimal. Okay, so all of these answers here are correct. Okay, so those are the absolute error in Taylor's measurement 1. Okay, and again, I just did these two side by side just to show you that one or the other. Okay, they both work exactly the same. Okay, and now Connor's measurement 1. Let's go ahead and look at his numbers. He had 15 4/8. Okay, absolute value of 15 4/8 minus 15, and of course that's going to be absolute value of 4/8, which is 4/8. Okay, and of course 4/8 is equal to 1/2 of an inch, which is also equal to 0 5/10 of an inch. Okay, all right, or 50 hundredths of an inch, right, if you wanted to. Okay, and again, these are all correct answers. Okay, just add an inch here, there. Yeah, okay, so all correct answers. So you can see it's a pretty simple process. Not much to be confused about, but what does get confusing is just this idea, and when these formulas like absolute value of a minus x. I mean, that might sound so weird, but the thing is, if you know what a is, you know what x is, there's no need to fear or fret. Okay, so let's go again. Let's do Jordan's measurement 2. Okay, look at Jordan's measurement 2, and that's 14 6/8. Okay. Okay, so let's go ahead and look at Jordan's measurement 2, and take a look at our absolute error here. Measurement 2 is 14 6/8. So if we go ahead and do that one, and again, absolute value of the approximate, which is 14 6/8, minus the exact. Okay, so it's going to give us an approximate value of absolute value of 2/8. Okay, or negative 2/8, which is 2/8, of course. All right. So again, and that 2/8 is going to be also be 0.25 inches. Okay. All right. So there we go. And yeah, that's it. I mean, seems pretty straightforward. It is straightforward. Just understanding the terminology, this idea of absolute error, and when it's used. That's what concerns me. That you know what the application of this is. It's not just something we just throw around, but it really does feel like it's been thrown into this lesson. But no, it's getting us to use once again our absolute value principle, which is a very, very important one. Okay, when we are determining, actually, truly the difference between 2 points in the sense. Okay, what is that distance between them? The distance between the exact measurement and that approximate, or that that measured measurement. Okay, what is that difference between whether or not it's a larger or smaller? They're still the same. That distance is the same. That error is the same. Okay. All right. So let's move on. Okay. So in this example 2, how right is wrong, we are going to now apply a different concept here, and that's this concept of percent error. Okay. So our task here in A is to find the percent error Taylor's measurement 1, which we've already calculated, okay? And then more importantly, what does this mean? And we'll discuss that after. Now, percent error, as you see down here at the bottom, excuse me, is defined as the percent error is the percent the absolute error is of the exact value. I know lots of words and really confusing just to read that without any explanation, okay? But it's simply taking that absolute error and just creating a percent error, okay? So we're trying to find out, what we're trying to find out in percentage terms is how close were we to the exact value. How close or how far away, okay, how far away. When you talk about that in unit terms, like we have already, we talked about a quarter of an inch, for example, for Jordan's second measurement, and actually Taylor's measurement, is also a quarter inch, okay? So we talked about 1/4 of an inch was the absolute error. Now that 1/4 of an inch is quite, what we say is relative, okay? It's relative because if that quarter inch error was made for something that was, 5-6 feet long, let's say, 1/4 of an inch out of 72 inches is not that extreme. Well, not as extreme as in this case where we have a 15-inch screen and we are 1/4 of an inch off, okay? That percentage is going to be a lot greater, okay? The percentage is going to be a lot greater in the case of the 15-inch screen. And hopefully that will become clear as we do these. So anyway, here we go. So the percent error, and again, of course, there's a formula here, okay, and that is, so sorry about all the coughing. The absolute value of the approximate measurement here and the exact measurement, okay? So the difference between those two, and of course that is that absolute value of a minus x over x, which is that exact value, okay? So that x, that exact value, is going to be our denominator, okay? We're going to divide those, and then we are going to multiply that by 100%. And the reason we multiply by 100% is simply to make a percent out of a decimal or a fraction, okay? All right, so let's go ahead and do that for Taylor. And like I said, we know that Taylor's error, okay, his error was 0.25, okay? So if we do, absolute value of, we won't figure that. We don't need to do that yet, but we're going to actually, in this formula here, we're going to plug in the values, okay? And we said that his first measurement was 15 2/8 inches, and then minus 15, which was the exact measurement, and divide that by 15, okay? And that, of course, this course is all absolute value of everything here, okay? And this was absolute value, therefore, of 2/8. I'm just doing this all over again, okay, just to let you know, over absolute value of 15, which was the absolute value of 0.25 over 15. This is all absolute value, okay? All right, so we can go ahead and do this division here, okay? The 0.25 divided by 15, okay? And then what we come up with, we can figure out our absolute error of that, okay? So if we go ahead and do this division right here, and again, you can do this, and I'm encouraging you now to go ahead and do that with a calculator, and that's of course going to be 0.25 or 0 25/100 divided by 15, okay? In lieu of that, if you really want to get some practice doing this freehand or doing this without a calculator, I mean, this
also could look like this: 1/4. We can make a complex fraction out of this. Okay, divided by 15, which we know is actually 1/4 times the multiplicative inverse of 15, which is 1 over 15. Okay, those of you who remember this, and that would be 1 over 60. Okay, so that's actually 1/60th. Okay, 1/60th. So our percent error in this case is 1/60th as a fraction. Okay, and then if we go ahead and do the division now, 1 divided by 60, which we would need to do to get our decimal, we would be looking at 0. I'm trying to think here. Let me 0.1. No, it's not 1. 0.01 and 3. No, I think it's like 6, 6, 6, 6. Okay. All right. So this is what we're going to get. If we divide 1 divided by 60, we're going to get something like this on the calculator. Okay. And then that would translate to, of course, because this is the hundredths place right here. All right. It would be 1, and let's use a fraction here. So that would be 2/3. So 1 2/3%. Okay. Which also could look like 1.67%. Okay, you could also show it that way. Okay, so our percent error here is 1 2/3%, which doesn't sound drastic. Doesn't sound like too bad. But again, I'm not sure exactly what is a good percent error, and we're not going to even discuss that in this lesson. But what we can discuss is what does this mean now? What does this actually mean? If I have a percent error here, Taylor's measurement 1 has a percent error of 1.67% or 1 2/3%. What does it mean? Well, what it means is that his measurement, okay, his approximation, his measurement was 1 2/3% off of the exact measurement. Okay, so it had a percent error of 1 2/3%. Okay, and again, you'll probably see this in the future in some more statistical applications. But for now, that's what this means. Okay, now I think it'd be a good time to have you practice a little bit of this. So I'm going to go ahead and pause and have you attempt B and C here, and see what you can get for those. And, come on back and we can check in, and then we'll talk once again about the about Part D here, what the purpose is of finding percent error. So go ahead and do those on your own, and come on back and check. Okay, so let's go ahead and check in and see where we're at. So let's see. So in Part B here, remember letter B. It says from example 1, Part B, find the percent error for Connor's measurement 1. Okay, and then of course, what does this mean? And if we go ahead and put that in its fractional form, of course, that's going to be his error. There was his absolute error was 1/2 inch or 0.5 inches, and we divide that by 15 inches, okay, and we get a decimal on our calculator that looks like that, 0.03333, and on and on and on. Okay, repeating decimal there. That is going to boil down to, of course, to either 3 1/3%, which is probably the preferable way to express this percentage, okay, or 3.33%. But again, for our purposes here in this pre-algebra class, I'd like you to default to the fractional version here, if you would. Okay. All right, so hopefully you did that well. We have part C here, letter C. We're trying to find the percent error for Jordan's measurement 2. And if we go ahead and write that out, it looks like that. Again, we have our absolute error on top, 0.25 inches, or a fourth of an inch over 15 inches. Works out, again, as we saw in the last problem, 0.016666, or 1/100th, or 16 thousandths, or on and on. Anyway, that of course boils down to 1 2/3%. Okay, 1 2/3%, because that's what this 6666 is going to be, equivalent to that 2/3%. Okay, so there we go. We have Jordan's measurement 2. So if we look at these and compare these right here, Connor's measurement 1 versus Jordan's measurement 2, we could see that that Connor had a greater percent error than Jordan had. Therefore, unlike what we're used to usually, the bigger the better. Truly, Jordan has clearly made the better measurement here. Okay, because he is only 1 2/3% off of the absolute value of the absolute measurement as as the actual or the exact measurement as is Connor. Okay, so he's closer in that sense. All right. Okay, yeah, or 1.67%. Okay, so this idea of what is the purpose of finding percent error, we've talked about this a little bit already in this video. But again, once again, it simply tells us, or tells you, or tells everybody how big our error, or your error, was compared to the actual value. Okay, how big it was. And again, I mean, this is it's very important. For example, an error of 1 centimeter is very large if you are a heart surgeon. Okay, but maybe not such a big deal if you're measuring out the course of a marathon, which is 26 miles long, 26.2 miles long. If you make 1 inch, if you're off by an inch, that is very, very minor. Okay, but if a heart surgeon is off by an inch, that becomes a very big deal. Okay, again, so in terms of which is more useful, your absolute error, which gives you a number, or your percent error, I would say we default to percent error as being the preferable measure of error. Okay. Okay, so here are exercises 1 through 3, and it asks you here to to calculate the percent error for these problems. Okay, and like I had said before, let's go ahead and leave our final answer in fraction form, and it says if necessary. Okay, if it's not a whole number, just leave it in fraction form. Just try to emphasize that fractional form. Okay, so I want you to go ahead and calculate the percent error for these problems, and come on back. Okay, so let's go ahead and check your answers and take a look at these percent error problems. Again, probably the trickiest thing. I mean, the process in this seems relatively easy. The formula is relatively straightforward, but the only issue I think will come up will be just translating these things. Leaving your final answer in fraction form, which can be a bit of a bear sometimes, especially for those of you who've become very, very used to your decimals. Okay, but really, again, really important to pay attention to the fraction form. We'll talk about that as we go. So, in this first problem, a realtor expected 18 people to show up for an open house, but 25 attended. Okay, so this idea of expected, okay, shows us that that's an approximation or an approximate. Okay, they expected. I mean, that's what they look for. And again, this is not, and as you notice from this problem, which is it's quite revealing. This is not only about like measurement. Okay, it's not necessarily a mathematical measurement. I mean, in this case, this realtor just estimated. Okay, expected 18 people, maybe 18 people signed up to come. Happens to us all the time when we have workshops here at the school. There's always a certain number of people we expect because they've actually registered. But what happens is maybe extra come or some don't come. So our actual attendance is often very different. Okay, and that idea of attended here, that's a key word here. That's the actual. Those are the ones that actually came. Okay, and again from there it's just a matter of setting this up. Absolute value of 18 minus 25 over 25, or the absolute value of 25. Okay, and again, that 18 comes from our expected. Okay, that is the approximate, minus the actual, which is the attended, over the actual. Okay, and if we go ahead and do that, we get the final analysis. Well, not final, but we get a fraction at the end of 7 over 25. And if we go ahead and do our division, we divide 7 by 25, we get 0.28 or 28 hundredths, and that is 28%. Okay, so the percent error for this realtor was 28%, and that's pretty far off. I mean, that could really throw you, because let's say you have you're expecting 18 people to come, so you have maybe you just you go, okay, let me bring 20 brochures, 20 pieces of information to give out there, but you're so far off, 28% off here. 25 came, and you're going to be short with your brochures. So always a little bit dicey when you're having to approximate. Okay, so our next one is a science class. This is more a measurement problem here. In science class, Mrs. Moore's students were directed to weigh a 300-gram mass on a balance scale. Tina weighed the object and reported 328 grams. Okay, 328 grams. Let's just go ahead and identify here the reported. Okay, so Tina weighed it. This is the student weighing it. She reported that it was 328 grams. That word is a key word in this sense for an approximate measurement or value. And there's no word here necessarily, but we just trust that a company that produces these mass weights, they are actually going to be true to what is stated on the actual mass. Okay, that's our actual. Okay, now the reason that Tina was so far off, okay, I mean, it could be many. Okay, could be many reasons for that, and many of them tied to where do you put all the different sliders on the scale. When you if you have a triple beam balance scale, if some of you know what that is, I have them in the lab. I work with kids with them, but you slide little sliders to measure the weight, and things can always go wrong. Okay, there's a myriad number of human errors that can be made. Okay. Anyway, let's get on with the math here. Yes, we go ahead and just plug our formula in. Absolute value of 328 minus 300 over that 300. And we end up with that, 28 over 300. Okay, and if we go ahead and punch that into our calculator, we get that 0.093333 and on, and that's going to boil down to 9 1/3%. So hopefully in the future, this is going to become absolute automatic for you. If you see these repeating threes trailing off on your calculator when you get your decimal, you will know that we are talking about 1/3. Okay, 1/3. All right, 1/3%. Okay, so number 3 is about a bowling tournament here. So Darwin's coach recorded that he had bowled 250 points out of 300 in a bowling tournament. However, the official scoreboard showed that Darwin actually bowled 225 points out of 300. So again, the words that clue us into what goes where in our formula. This idea of Darwin's coach recording. Okay, so this is a human being taking a measurement or taking a score. That's going to be the approximate. Actually, we have an official. Actually, this is probably even a more important word here, but we have an official scoreboard that showed that Darwin actually bowled 225 points. Okay, so that was going to serve as our actual value. Okay. Again, setting up our equation. Okay, absolute value of 250 minus 225 over 225 or divided by 225 is going to give us that 25 divided by 225, which actually I went ahead and made a fraction out of it because I saw the relationship right there. 25 goes into 225 9 times, so I know that actually is 1/9. And what's interesting about 1/9 is 1/9 gives you a bunch of ones, okay, after the 0 there. So 0.011111111, okay, which is going to give us 1 1/9, okay, 1 1/9%. And this is one of those that it may not seem so clear that it's 1/9%, but as soon as you're going to go over here in your decimal, okay, so you know that at the hundredths place, that's going to be my 1% right there. This is my 1%. Okay, then the rest of these are going to be repeating ones. Okay, whenever you see those repeating ones after your first percentage, and that could be right there after your hundredths place. If you see those repeating ones, you know that that's going to be 1/9 as your fractional percentage piece. Just like the repeating threes are going to mean 1/3, the repeating ones are going to mean 1/9, and we also know that repeating sixes mean 2/3. Okay, so that's how we translate those. And again, that will become more and more of an automatic for you as you move along. Sorry, I didn't know you were there. I was sniffing here, looking at at my pages. Yes, anyway, here we go. So this example 3 is estimating percent error. Okay, so the idea here is for you to actually see that sometimes percent error can only be estimated, not necessarily calculated. Okay, so sometimes the exact value is not necessarily known. Okay, but is known to lie in an interval. So between two numbers, and in this case right here, we could just read this here, help us out. The attendance at a musical event was counted several times. All counts were between 573 and 589. Okay, so if the actual attendance number is between 573 and 589 inclusive, what is the most the percent error could be? Okay, then you go ahead and we'll talk about explaining your answer here. So if you want to go ahead and try to grapple with that, maybe not. Let's just do it together. Okay, so here we go. So we have to look at we're looking at the most, what is the most the percent error could be, okay? So we're trying to find the worst case scenario, all right? and the worst case scenario, or the highest percentage error, would be between these two numbers, the minimum and the maximum. Okay, so all we would have to do then is just find the, and we can use either one of these. Okay, the absolute value of 573 minus 589. Okay, because we've taken the lowest and the highest. Okay, because we know that's our range right there. Okay, and we divide that by we could put the actually, to give us our greatest error, that would be the lower number. Okay, so again, this takes a little getting used to. Okay, because we're going to have 16. That's going to be 16 because that's going to be the absolute value of negative 16 right here. Okay, which is 16. Just trying to cut to the chase there. 16 over 573. Okay. Now, if we had, let's just go ahead and say we do it a different way. If we go ahead and do this, and let's go ahead and let's just compare. Let's put 589 on the bottom. Okay. And you could probably see this already, that our greater percentage error is going to come from this one where our denominator is smaller. Okay. But let's just go ahead and do it. Just go ahead and punch these into the calculator. I'm going to go ahead and pause and do that right now. Okay, so hopefully you did that as well, and if you did, you would have noticed that 16 divided by 573 would have given us 0.0279, what's that, 279 10,000ths or whatever. It kept going on. But we would just round that down to 2.8%. Okay, 2.8%. And now you also would have noticed that the other one wasn't very much different. Okay, 0.02716, on and on and on and on, which is going to yield us a 2.7% error. Okay, again, not very, very far off. Okay, because these numbers are relatively close, but this one here, that scenario would have given us the greatest percent error. So in this case, it would mean that 573 people actually showed up, okay, and the range was 16 people if we had estimated or approximated 589, okay, and this would have been our greatest percent error. Okay, you could also calculate like a minimum and a maximum. Okay, a minimum and a maximum percent error. Okay, in this case it would have been minimum would have been 2.7%, maximum 2.8%. Okay, so here we are at our lesson summary. We are at less than 50 minutes right now. We're gonna probably won't make it. I'm sorry, I do talk too much, but anyway, I just want to go over this. And again, something that may seem obscure to you, this whole idea of absolute error, percent error, but hopefully you can have fun with them. The formulas are not that difficult, truly. Again, practicing, recognizing decimal values as fractions, like the repeating ones as 1/9 and the repeating threes as 1/3. I think that's something I would wish for you to do more automatically in the future. Okay, so here we go. Lesson summary. The absolute value is defined as a minus x. Okay, and that x, of course, is the exact value, the actual value. Other words to use for that: exact or actual. Okay, of a quantity, and a is that approximate value. That was the one that was estimated or expected or recorded. All those kinds of words that show us it's an approximation. Okay, and percent error, just very simply, is just taking that difference or that absolute error and just dividing it by the actual measurement. And again, this whole times 100% here kind of bugs me, but it's just to show you how, if you wanted to, you can just do that division, then multiply by 100, and you'll end up with your percentage, okay? But you should know how to look at a decimal and make it into a percent, okay? That's something I want you to do automatically on your own, okay? Now, the absolute value will tell you how big the error is, okay? How big the error is, but percent error compares the error to the actual value, okay? And of course, makes very good sense. A good measurement has a small percent error, okay? And that's not always very easy to do, especially when you're working with things that are very, very small, okay? Measurements that are very, very small, or when you're working at, projecting how many people will show up at your real estate open house, okay? It's not always easy, but that's one thing we try to do in business, in manufacturing, and in real life, is to decrease or get our percent error down to the minimum possible percent error. Okay? Anyway, yeah, that's how that applies to our lives, and hopefully you had some fun with this. Any questions ever, just give me a call or send me an email. Okay, have fun.